Our next speaker hates cacophony as much as Matthew. It's all about the euphony. He uses customized algorithms, really high-end software to make places sound amazing. He's the founder of One-to-One Computational Geometry, which advises firms on really complex design problems. He's worked with Arup, Herzog and de Meuron. And his current project, which he'll say a bit about, is this new concert hall in Hamburg, which is an incredible building. And Benjamin's, making it sound good. So, Ben.
Thank you. So I'd like to just say a few things about just sound in general, because in the way it relates to architecture. The word sound is the overall term for both music and noise, and this distinction between music and noise, one being an art form and the other being the sound of a fan, like was just pointed out, is nowhere more evident than in architecture, because acoustics is one of the most undervalued senses in the designing of buildings. And so I've been very lucky to work on a few projects which work on the acoustics of spaces, and our office is essentially working on the realization of the project. So we work a lot with materials and how they affect the acoustics. I can't talk too much about the specifics of the design projects because they're still under construction, but just as a broad idea, it's about the way that sound propagates through the space. When somebody designed this building, I think they had more the visual aspect of the sort of fake wood panels in mind, or the clean roof, and not knowing what kind of effect it has on the acoustics of the space. So what acousticians do a lot in architecture is what's called noise reduction, and I think that's kind of it's a little bit sad that there's not more work being done on creating better spaces rather than just reducing the noise in terms of the sound. So what we are working on is how the geometry affects the kind of sound diffusion of the sound waves that are hit by a wall. So a clean wall has a very bad acoustic properties. The sound waves just hit it like a billiard ball with at the same angle that it hits it, it gets reflected back. So when you look at the back of the building, of the room, there's this more textured wall where this actually diffuses the sound. So the sound waves, which have different wavelength, and you can actually calculate all of this, hits the surface, and because it's very undulated and very rough, it doesn't get reflected the same way, but it gets scattered around the room, and that's a very favorable property for the performance of music. I think that as I said, I can't talk too much about the Hamburg project because I've been asked not to until it's finished, but just as a general note, I think maybe I'll talk more a bit about the potential that's out there, because the way that the work was done is that you get some sort of specifications about depth, about the geometry that a surface has to have in order to have these properties. And we actually worked a lot on developing programs which could actually link, and I think that's sort of the most interesting approach. What we can offer is that you can actually make a link between the software program which produces the geometry of a wall surface, and then link it to an acoustic program which actually tests it. Which at the time when I was working on these projects, the software didn't exist. Well, I was told it did exist, but it's sort of not done in the industry, and people said, well, we've done it this way since 50 years, and we'll just keep it that way. And I think there was a great potential about actually creating this parametric model of a space where you can define parametrically all the geometry of the concert hall, or even a regular space, all the surface qualities, even the geometry down to the millimeter, and then actually create a feedback loop, testing it, optimizing it, and I think that's really something that should be done in the next few years, because I think there's a great potential for that, and creating not only better concert halls but better spaces in general in architecture. Thank you.
Thank you, Ben.